I copied the code of the vesting module into a new module called Parameterized, and I want to talk about parameterized contracts next. So note that in this example, we use this vesting datum type as datum, but the datum was just fixed. It was just sitting there. It didn't change. And alternatively, we could bake it into the contract, so to speak. So we can write a contract where the script itself already contains this information, beneficiary and deadline. So all the examples of contracts we have seen so far, they were always fixed. So we had this typed validator, and that was just of type typed validator. So it's a constant, a compile time constant actually. So the idea of parameterized scripts is that you can have a parameter. So depending on the value of the parameter, you get different values of typed validator. So instead of just defining one script, you, so to say, define a family of scripts that are parameterized by a given parameter. So I want to demonstrate how we can do this here by, instead of using datum for these two pieces of information, using a parameter, so that the contract will be parameterized by this. So in order to do that, vesting datum is no longer appropriate name. So let's call it vesting param instead. And then we don't need the datum is data instance anymore. So let's remove that. Now this has to change. This now gets an additional parameter, namely the parameter of the script. So vesting datum. And now comes the datum. And because all the information we needed until now in the datum is now contained in this param here, we can simply use the unit type as datum. So this is now one parameter more, the parameter of the script. So by picking a specific value of this parameter, I get what I had before of type signature, datum, redeemer, context to bool. And the code, of course, has to change a little bit, but not much. So let's call the parameter argument p. And instead of det or dat, we now just have unit. And now all I have to do is I have to exchange all the dats for p's. So here, p and here. Okay, so small change. Now this vesting type also has to change because now the datum type is no longer vesting datum, it's simply unit. Now we have to think what to do here. So this is now no longer just a constant, this typed validator. It now takes the parameter. So vesting param. So let's put that here. And now the question is what to do with this. So the function make typed validator expects as its first argument the compiled code of something of type datum to redeemer to context to bool. But now this make validator doesn't have this type anymore because it has this extra parameter p. So this wouldn't work like that. What we would like to do, before I forget, I must change this to unit as well. So what we would like to do is put a p here. Now the type would be correct, or it looks like that, because p has this vesting param type. So if we apply make validator to p, we apply the first argument here, and what we are left with is something of type unit to script context to bool, which is a suitable type for this make type validator function. Let's leave it like this for the moment, and let's just change the rest, because now all these things are no longer constants. Validator now also takes a parameter. And instead of doing this, we have to compose it with typed validator. So actually, I mean, to write that like more explicitly, we would have this p here, and then we would have to apply the p first to type validator to get a type validator, and then we can apply validator script. But in Haskell, in simple cases like that, we like to do it point free, so we use function composition instead. Same for validator hash. That now also takes the vesting param type. And same thing, must replace that with function composition. And script address as well. It's now also parameterized by this parameter. However, if we go to the REPL, then we get a compiler error. And it says reference to a name which is not a local, built-in, or an external inlineable function variable p, no unfolding. And the problem is this. And as I explained when I explained the template Haskell and these Oxford brackets and the use of this inlineable pragma, I said that everything in the Oxford brackets must be known at compile time. It must be explicitly known. So normally it would even have to be explicitly included, written inside these brackets. But by using this inlineable pragma, we can also have it in external functions like our make validator. But it must still be known as at compile time, because that's how template Haskell works. It is run, it's executed before the main compiler, the Haskell compiler, is run. So at compile time, template Haskell, in order to do this, to compile to Plutus core, must know what is inside these brackets. But the P, of course, is not known at compile time, because we intend to, at runtime, provide some arbitrary value of type vesting param and then apply this function type validator to it. So the P will only be known at runtime, and therefore this can't possibly work, even though the types look correct. Luckily, there's a way around that. So what's the situation? On the Haskell side, we have our make validator function, and we have the P of type vesting param. And we could apply the one to the other like this. And that would have the right type. Now on the Plutus core side, we can compile this because make validator is known at compile time. And I don't know how to write this. Let's, for example, put it into angular brackets to indicate that this is compiled to Plutus core version of the Haskell function make validator. And I want this. I want make validator P compiled. But I can't apply compile here because the P is not known at compile time, so template Haskell won't work for P. So I can't do that. So now the idea is, in Plutus, this angular brackets make validator is also a function. It's not a Haskell function anymore, it's a Plutus core function, but a function nevertheless that you can apply to arguments. So if I could get my hands on the compiled version of P, then what I could do, I can't do this here directly, but then I can simply apply the make validator compiled, and actually that is called apply code in Plutus code to P. That would then be what I want. That would be the same as this. But this looks as if it doesn't solve anything because we still need a compiled version of P. And we have the same problem that P is not known at compile time but only at runtime. However, P is not some arbitrary Haskell code, it's data. So it doesn't contain any function types. And as we will see, for such types, there is a way, if we make the type of P an instance of a type class called lift, that's called lift code, that does work at runtime. So using lift code, we can compile P at runtime to Plutus core, and then using apply code, we can apply this function, this Plutus core function, to this Plutus core value to get this, which is exactly what we want. Let's briefly look at the lift class. It has one method, lift, but we won't use that method directly. As I mentioned before, we will use something called lift code. But lift code is available for types A that implement this lift class. And we see there's a bunch of instances for it. We can ignore this uni type parameter here. But we see it's all for data. It's characters, byte strings, integers, booleans, unit, data. I don't actually know what square root does. Lists of things that have an instance, maybe, ratio, and so on. Either, pairs, maps, triples, quadruples, quintuples, but no functions. And that's the reason why we can't use lift code all the time, not for compiling Haskell validators to Plutus core validators. But we can use it for these data-like types that are similar to the data type that we use to express our datum and redeemers and the script context. So for those sort of types that are data-like and not function-like, instances for the lift class are available, and then we can use lift code. So let's have a brief look at lift code. We can ignore the second and the third precondition here. So if we have lift of A, then we have a function from A to compile code of A. And that's exactly what we need. So if we go back to the code, we can't do this, as I said, but we can use Plutus.tx apply code and now lift code P. However, this won't compile, or it's probably Plutus.tx lift code. However, this won't compile because now the compiler complains that we don't have a lift instance for vesting param. But there, something similar is true as what I said about isData. There is a template Haskell mechanism to automatically get such an instance. So we can do Plutus.tx make lift and vesting param. Now we get another error, illegal instance declaration, use multi-param type classes. That is because we saw this lift class had additional type parameters. So in standard Haskell 98, you can only have one type parameter for a class, but lift uses more, and that is enabled by this extension. So we have to add this to our extensions. Try again. It compiles. Now let's briefly look at the off-chain code, which hasn't changed much, but somewhat. So the give parameters are still the same. I must know the beneficiary, the deadline, and the amount. The schema has slightly changed. The one for give is still the same, but for grab, we now need to know the deadline, because in order to find the UTXOs of gifts that are locked at that script, now because the script address depends on these parameters, the beneficiary and the deadline, we need those in order to find the UTXOs. We know the beneficiary, that will be the pub key hash of the wallet that calls grab, but we can't know the deadline. So I made that a parameter here. So the gift endpoint is very similar. So instead of computing the datum, we just define something of type vesting param. And then this must pay to the script. Now the datum is just unit. And here when we submit the transaction, now the type validator is no longer a constant, so we provide this parameter P that we defined. The rest is the same. Grab is now different. Recall earlier, we got all the UTXOs sitting at this one script address. And that could be for arbitrary beneficiaries and for arbitrary deadlines. So we had to filter those UTXOs that were for us and where the deadline had been reached. Now the situation is different, so we again check what is now, and we check our own public key. And now we do know the deadline in advance because it's a parameter to this grab. So we can immediately see whether the deadline has been reached or not. So if it has not yet been reached, we simply log a message that it's too early and stop. If it has been reached, we can compute the vesting params. We have the beneficiary and the deadline, and we look up the UTXOs at this address. Now address again is not a constant anymore, but takes this parameter. So now we will only get UTXOs that are for us and for this deadline D. And we know that all of them are available, so we don't have to filter anything because we already checked that the deadline has passed. So all we do is we check whether there are none, and if there are none, we don't even bother and just say no gifts available. And if there is, then we do more or less what we did before. So we define the lookups that define these UTXOs and the script. And the constraint is that we want to spend all those UTXOs that we found, and that it must validate in the right validity interval. And we submit as before, wait for confirmation, and log a message. Endpoint is only slightly different now here in grep because we have this one parameter. Let's briefly try this in the playground. So I already copied the code and I also already set up the simulation. So let's go through it. So first I created an additional wallet, and wallet 1 will give to wallet 2 and 3 at various deadlines. So first wallet 1 gives to wallet 2. So as I explained before, I looked up the payment pub key hash, and this is the beginning of slot 10, this number. So the first gift, and all the gifts will be over 25 ADA. So the first gift is from wallet 1 to wallet 2, deadline slot 10. I wait, then wallet 1 gives again to wallet 2, but this now is deadline slot 20. Wait again. Now this is wallet 3, deadline slot 10. Again 25 ADA. So there are 3 gifts, 2 to wallet 2, 1 to wallet 3. The 2 for wallet 2 have deadline slot 10 and 20, and the 1 for wallet 3 has deadline slot 10. I wait until slot 11, then wallet 2 grabs, and this is now different to before. Earlier our grab didn't have any arguments. Now we have to specify the deadline. So this is 10. So wallet 2 tries to grab for 10. And at the same time, because they are independent, so we can do that simultaneously, wallet 3 also grabs for the same deadline for 10. Then we wait until slot 21 and wallet 2 grabs again, but now for slot 20. And we wait a bit again and see what happens. And note that now it's no longer possible for one wallet to grab more than one gift at the same time. At least not more than one gift that isn't for the same deadline. Earlier that was possible, so if we had waited, if wallet 2 had waited until slot 21 and done a single grab, it would have picked up the gift for deadline 10 and the gift for deadline 20. But now we have to do this separately because we specify the deadline we are looking for as an argument to grab. So let's see whether it works. It seems to have worked. So let's briefly go through the transactions. Genesis, first gift to wallet 2, deadline 10. Second gift to wallet 2, deadline 20. Gift to wallet 3, deadline 10. Now at slot 12, we see this is wallet 3 picks up its gift, and wallet 2 picks up its first gift. Finally, in slot 22, wallet 2 picks up its second gift.